And now we go to part 3 of ANOVA. In this portion, we're going to be talking about post hoc tests. And so post hoc tests are used to determine which groups have significant differences between them. Now, if there are no a priori predictions, what that means is if you have no idea previously or prior to data analysis about the differences that might be there, and instead you want to do exploratory differences, you might do post hoc tests. And post hoc tests use pairwise comparisons. And what this means in English is kind of looking at t-tests between group combinations. But remember, there was a problem with doing t-tests, and that's the same problem when we're looking at post hoc tests, which is that we can run the risk of inflating the chance of error because we're just doing these multiple tests that have 0.05, all of them, as set as your alpha level. So this is corrected by controlling for significance level. So the easiest way to do a post hoc test is to use a Bonferroni correction. And that's where you take your 0.05 criterion and divide it by the number of comparisons you're going to be looking at. So the critical p-value is now the alpha divided by k, the number of comparisons you are going to be using. So if we had 3 groups, your new critical value would be 0.017 instead of 0.05. So now, instead of having a 5% chance of saying that there is a significant difference when you are incorrect, it's now down to a 0.017%. And so that just means that we're getting stricter and stricter because we are doing more and more tests. So the consequence of this is a loss of statistical power. It's harder to find differences between groups because you have this smaller p-value. That's why we don't have the criterion set at 0.017 to begin with, in part at least, is we want to be able to find these effects. But also, what this ends up doing is it increases the chances of a type 2 error, where you say there is no significant difference, but in fact there is. So when you do a Bonferroni correction like this, you are actually increasing your chance of type 2 error by kind of decreasing your chance of type 1 at the same time. These things commonly go hand in hand. So let's look at an example. If you wanted to see if children who wear different superhero costumes get more injured, or which ones do, then we would have to do comparisons between costume choices for Ninja Turtles, Hulk, Superman, and Spider-Man. We'd have to do all of those comparisons. So we measure how severe the injury is across the groups, and we get the following data. Now, because we have 6 comparisons, so Ninja Turtle and Hulk, Ninja Turtle Superman, Ninja Turtle Spider-Man, that's 3, Hulk Superman, Hulk Spider-Man, 2, so 5 total, and then Superman Spider-Man, that's 6 total. Well, we take our 0.05 criterion, divide it by 6, and we get 0.0083. So now, even if we had our p-values, our original ones, when we look at the Bonferroni correction, what happens is some of them are still significant. So there is a difference between Ninja Turtles and Superman, or Superman and Hulk, but 2 of the values that we would have originally thought to be significant, because they're less than 0.05, are no longer significant because they're not below 0.0083. So we can see here that there's a bit of wiggle room in this middle, this gray area, where it's not significant enough for the Bonferroni correction, but it's also not significant enough with the just regular p-value to bump it down. So there are more than one type of post hoc test, and which one are you going to be doing? Well, it's whoever your advisor or your boss or reviewers or whoever tells you, or it's how conservative you want to be. But I don't care right now that you're able to calculate any of these. I want you to understand them. And so one other example is instead of Bonferroni, it's a home criteria. So in that case, what you do is you try to control for global p-value as opposed to for across all of them. And some people are okay with this. So in that case, we would see that this Ninja Turtle Spider-Man comparison, which we thought was originally significant, is still not. But the Spider-Man Superman is getting closer now with this different kind of criteria. So based on the criteria, you can actually have differences in what you consider significant. And this is why there can be such debate among academics and people over which one to use. So this is more meant as a cheat sheet if you ever come back for some reason you want to figure out which one you want to use. Well, here you go. So there is always this trade-off in statistical power and type 1 error. So if you're more conservative, you lose statistical power, so you could lose real differences. So Bonferroni controls for type 1 error very well, but it's very conservative. Whereas Tukey, on the other hand, it controls type 1, but it's better when you have a large number of means, when there are a bunch of comparisons you want to do, at least better than Bonferroni. Home, on the other hand, gives you more power, but doesn't control type 1 error quite as much. And the Benjamini-Hochberg correction does not control for type 1 rate, but instead looks for false discovery rate, which is kind of a different can of worms. Again, I don't want you to memorize these. You don't need to know them for me. This is meant to be a reference so you can see what you might use. And now I'm going to show you in SPSS what it'll look like to actually run some of these things so you can actually see how you could interpret them in the end. So in the example we're going to look at, I've got the pet group. It's the example from the previous lecture, and agreeableness. So we have a situation in which 1 is cat, 2 is dog, and 3 is horse, and we have their agreeableness. So if we run our ANOVA, we're going to have our factor, that's just the grouping variable. The dependent list is the continuous variable we're looking at. Then we would look at post hocs. And so you can pick, there's a ton of them. So let's say we want to do Tukey and Bonferroni and Sheffy just to start. So we can hit continue, and then when you run them, you'll see that you'll get a bunch of different comparisons. So we have our ANOVA here that gives us the same sum of squares, the same total sum of squares that we saw previously. But then we can come to our post hoc test and we can see the differences for Sheffy, Tukey, Bonferroni, and it will give us any significant differences between them. Now it turns out we don't in this case, but this is what you would look at, and this would not really matter. But you'd look in here to see what the mean differences are and which ones are significant.